Polar graphs. The graphs of r equals a times the sine of theta and r equals a times the cosine of theta are circles with diameter equal to the absolute value of a. So here we have the graph of r equals a times the cosine of theta. A few things you should notice is that the diameter is actually equal to the value of a. You should also notice it's tangent to the y-axis and that it's symmetric to the polar axis. So as above, so below. That's because of the cosine. Here we have the graph of r equals a times the sine of theta. It's still tangent, but in this case tangent to the x-axis. The diameter is still a, but that diameter is along the y-axis now. And instead of being symmetric to the polar axis, now it's symmetric to the line theta equals pi over 2, or the y-axis. So let's take a look at an example. Here we have graph the polar equation r is equal to 6 times the sine of theta. So a few things. We see here that the diameter of the circle is going to be 6. So it's going to be tangent to the x-axis because it's a sine and have a diameter of 6. And it's going to be symmetric to the line theta equals pi over 2, or the y-axis. So let's go ahead and plug some numbers in and see what this thing looks like. So if I plug in 0 for theta, well, the sine of 0 is 0, and 6 times 0 will also be 0. So I get the pole there, 0, 0. So I'll plot a point at the pole, 0, 0. Next, I'm going to plug in pi over 6 as the angle. So when I plug in pi over 6, the sine of pi over 6 is half, and 6 times half is 3. So I get the point pi over 6, 3, and I'll plot that point. Then I'm going to plug in pi over 4. When I plug in pi over 4, I get the sine of pi over 4 is the square root of 2 over 2, times 6 will be 4.24. So I'll graph that point, pi over 4, 4.24. And then I'm going to plug in pi over 3, this next angle. At pi over 3, I'm going to get 5.20 when I plug it in, because the sine of pi over 3 is the square root of 3 over 2 times 6 is 5.2. So I'll plot that point. And then lastly, I'm going to plug in the quadrant angle, pi over 2. So at pi over 2, I get the sine of pi over 2 is 1, and then 6 times 1 is 6. So I get the ordered pair right there at pi over 2, 6. That's the last one I'm going to plug in, because now I can get a basic idea of the shape. Let me connect these dots with a smooth curve. And I know that this is a circle that's going to be symmetric to the line theta equals pi over 2. So to graph the rest of it, all I have to do is graph a mirror image on the other side. And there is the graph of r equals 6 times the sine of theta. It's just a circle. All right, another type of polar graph we can have is the graph of a limison. So let's take a look at that. The graphs of r equals a plus or minus b times the sine of theta and r equals a plus or minus b times the cosine of theta are called limisons. You'll notice that there's two terms here, a constant and then a term that has a sine or a cosine with a coefficient. That's how you can identify limisons. And it turns out that the ratio of those two constants, a and b, determines the shape of the limison. So if a over b is less than 1, we have a limison with an inner loop like this. Or you can say the absolute value of a is less than the absolute value of b. So a is the smaller number. In the case where a and b are the same number, or opposites of each other, then we get this shape called a cardioid. So the cardioid is when a and b have the same absolute value. And then in the case where the absolute value of a over b is between 1 and 2, so it's bigger than 1 but smaller than 2, we get what's called a dimpled limison. You see the dimple over there. And in the case where a over b is greater than 2, we get a limison with no dimple and no inner loop. So those are the 4 cases that we can have with limisons. Let's take a look at an example. So in this example, we have r equals 2 plus 4 times the cosine of theta. A is 2, b is 4. The ratio of a to b is 1/2, which is less than 1. Whenever you have a ratio of a to b less than 1, we know we're going to get a limison with an inner loop. And because we're graphing a cosine here, we know it's going to be symmetric to the polar axis. So as above, so below. We only have to graph either the top or bottom half and then reflect it to get the other half. So let's go ahead and plug some numbers in. If I plug in 0, the cosine of 0 is 1. 4 times 1 is 4. 4 plus 2 is 6. So if I plug in 0 for theta, I get 6 for the radius. That's this point here. And then I'm going to plug in pi over 6, that angle. So if I plug in pi over 6, the cosine of pi over 6 is the square root of 3 over 2. When you multiply that by 4 and add 2 to it, you get 5.46. Then we graph that point, and then we can connect those dots with a smooth curve. Now I'm going to plug in pi over 3. So when I plug in pi over 3, that's the cosine of pi over 3, which is half. 4 times 1/2 is 2. Then 2 plus 2 is 4. So I get this point here. And then I'm going to connect those with a smooth curve. Now I'm going to plug in the quadrant angle pi over 2. If I plug in pi over 2, that's the cosine of pi over 2 is 0. 4 times 0 is 0. 0 plus 2, 2. So I get the point pi over 2, 2. Connect those with a smooth curve. And now, because I'm so close to the pole, I'm going to plug in two angles. I'm going to plug in 7 pi over 12 and 2 pi over 3 just so I can get some resolution to see what's going on there. When I plug in 7 pi over 12, I get 0.96, which is very close to the pole. And when I plug in 2 pi over 3, I get 0, which is actually at the pole. So those are the 2 points right there. Connecting those with a smooth curve gives me that. And I'm going to plug in 2 more since I'm still close to the pole. I'm going to plug in 5 pi over 6 and pi. So when I plug in 5 pi over 6, I get a negative radius, which means at 5 pi over 6, I'm going to go across the pole to graph negative 1.46. And at pi, I'm going to go across the pole to graph 2. So I get those 2 points right there. And I can connect those with a smooth curve to get this curve right here. This is the top half, so I don't have to plot any more points of my limison. And if I want the rest of the graph, I just mirror this. So as above, so below, I'll get this limison here. And as you can see, because the ratio is 1/2, I do have that inner loop. So a limison with an inner loop. The next kind of polar graph I want to look at is called a rose curve. So the graphs of r equals a times the sine of n theta and r equals a times the cosine of n theta, where a is not equal to 0, are called rose curves. If n is even, the rose curve has 2 times n petals. If n is odd, the rose curve has n petals. So here we have the graph of r equals a times the cosine of 2 theta. Because it's a cosine, it's symmetric to the polar axis, so as above, so below. The value of a gives you the maximum distance from the pole. The 2, well, that's the value of n, and since it's even, that means there's 2 times n, or 2 times 2 petals, 4 petals. 1, 2, 3, 4. Next to it, we have the graph of r equals a times the sine of 4 theta. Once again, the maximum displacement is a. Because it's a sine, though, instead of being symmetric to the polar axis, which this actually is, but it's also symmetric to the line theta equals pi over 4. And because n is equal to 4 and it's even, there's going to be 2 times 4 or 8 petals. 1, 2, 3, 4, 5, 6, 7, 8. Next to it, we have r equals a times the sine of 3 theta. This is the first one we're looking at with an odd value for n. Once again, though, a is still the maximum displacement. The sine still makes it symmetric to the line theta equals pi over 4. But because, once again, n is an odd number, there's exactly n petals. 1, 2, 3 petals, and n is 3. And here another case of an odd value for n. N is 5 in this case, and I have 1, 2, 3, 4, 5 petals. A is still the maximum displacement because the cosine is symmetric to the polar axis, as above, so below. So let's take a look at an example. Here we're going to graph the polar equation r equals 6 times the cosine of 2 theta. Because it's a cosine, I know it's going to be symmetric to the polar axis, as above, so below. So I either draw the top or bottom half and just mirror it to get the rest. The maximum displacement is going to be 6. That's the furthest I'm going to be from the pole. And there's going to be 4 petals because 2 is an even number. So let's plot some points. If I plug 0 in, the cosine of 0 is 1. And 6 times 1 is 6. So I get the point 0.06, which is out here. And then I'm going to plug in pi over 6. So when I plug in pi over 6, that's the cosine of 2 times pi over 6. 2 times pi over 6 is pi over 3. And the cosine of pi over 3 is 1/2. 6 times 1/2 is 3, so I get the point pi over 6, 3. And I plot that point and connect those dots with a smooth curve. Then I'm going to plug in pi over 4, this angle here. When I plug in pi over 4, well, that's the cosine of 2 times pi over 4. 2 times pi over 4 is just pi over 2. And the cosine of pi over 2 is 0. So 0 times 6, still 0. So that's the pole. And then I'm going to connect those with a smooth curve. Next, I'm going to plug in pi over 3. When I plug in pi over 3, I get the cosine of 2 pi over 3. And the cosine of 2 pi over 3 is actually -1/2. And -1/2 times 6 is -3. So I get pi over 3, -3. So here's pi over 3. And I go across the pole to graph -3. And there it is. Connecting those with a smooth curve gives me that. And now after pi over 3, I'm going to plug in the quadrant angle pi over 2. So I plug in pi over 2. The cosine of 2 times pi over 2 is the cosine of pi. Cosine of pi is -1. So 6 times -1 is -6. And I'm going to graph pi over 2. But because it's a negative radius, I go across the pole to graph -6. So there it is, pi over 2, -6. Connecting with a smooth curve gives me this. Next, I'm going to plug in 2 pi over 3, just beyond that quadrant angle, 2 pi over 3. When I plug in 2 pi over 3, I'm going to get the cosine of 2 times 2 pi over 3, or the cosine of 4 pi over 3, which is -1/2. 6 times -1/2 is -3. I'm going to plot that point, 2 pi over 3, but I have to go across the pole to 3 and plot it there. Connecting those with a smooth curve, I get this. And now I'm going to plug in, after 2 pi over 3, I'm going to plug in 3 pi over 4. Plug in 3 pi over 4, I get the cosine of 3 pi over 2, which is 0. 6 times 0 is 0. So I'm back at the pole. I'm just going to connect with the pole. All right, so now I'm going to plug in, after 3 pi over 4, I'm going to plug in 5 pi over 6. So I plug in 5 pi over 6, I get half. Half of 6 is 3. So I'm going to plot that point, 5 pi over 6, 3 right here, connect with a smooth curve. Lastly, I'm going to plug in pi. When I plug in pi, I'm going to get the cosine of 2 pi, which is 1, and then 1 times 6 is 6. So I'm going to graph pi 6 right there. There's pi 6. Connecting with a smooth curve, I get this. And then now I have the whole underside. I've gone all the way to pi. If I go back all the way through to 2 pi, I'm just going to repeat this same pattern except underneath here. So it's going to look something like that. So I just draw that in, and there it is. There is my rose curve with 1, 2, 3, 4 petals and a maximum displacement of 6 that's symmetric to the polar axis. All right, last kind of graph I want to look at is the graph of a lemniscate. The graphs of r squared, so that's different, equals a squared times the sine of 2 theta, and r squared equals a squared times the cosine of 2 theta, where a is not equal to 0, are called lemniscates. And we have here 2 of them. And you'll notice once again that the maximum displacement is still the value of a, even though it's a squared that shows up in the equation. You'll also notice the cosine is symmetric to the polar axis, as above so below, and the sine is symmetric to the line theta equals pi over 4. Maximum displacement is still a though. Let's look at an example here. Graph the polar equation r squared equals 36 times the sine of 2 theta. Well, since it's a sine, it's going to be symmetric to the line theta equals pi over 4. So I only really need to graph half of it. The maximum displacement is going to be the square root of 36, which is 6. So let's plot some points. So if theta is equal to 0, I get the sine of 2 times 0 is still the sine of 0, which is 0. So I have that when theta is 0, I'm going to be graphing the pole. Now I'm going to plug in pi over 6. When I plug in pi over 6, well, that's the sine of pi over 3 times 36, but that's equal to r squared. So I take the square root of that, and I get 5.58. And I'll plot that point. Then I'm going to connect those with a smooth curve. So connecting those with a smooth curve gives me that. Now I'm going to plug in pi over 4. So pi over 4. When I plug in pi over 4, I'm going to get 6. But I knew it was going to be symmetric to the line theta equals pi over 4, and that the maximum displacement was going to be 6. So that was almost known. And then I'm going to connect those with a smooth curve. Then I'm going to plug in pi over 3 now. When I plug in pi over 3, I get 5.58, which I should have guessed because this thing is going to be symmetric to that line. So it looks like that. And then if I plug in pi over 2, well, that's the sine of 2 times pi over 2, or the sine of pi. Sine of pi is 0. So I get 0 here, and I'm back at the pole. So that's one part of it. That's one pedal of this lemniscate. So let's go ahead and continue plugging numbers in. For instance, I notice that when I plug in 2 pi over 3, 3 pi over 4, and 5 pi over 6, the sine values I'm going to get are going to be negative. Because when I double, for instance, 2 pi over 3, I get 4 pi over 3, which is down here, which has a negative sine value. So that means for all these angles in the second quadrant, the answer to this is going to be an imaginary number. It's going to be a non-real value. So therefore, none of the values in the second quadrant are actually going to produce any ordered pairs. So now I'm going to skip all the way down to the third quadrant. I'm going to start with the quadrant angle for that third quadrant pi. When I plug in pi, well, the sine of 2 pi is 0, so I get 0 again. So I'm still at the pole. Still at the pole. So I'm going to plug in another number. I'm going to plug in 7 pi over 6. This one in the third quadrant here. When I plug in 7 pi over 6, I actually get the sine of 2 times 7 pi over 6, which is 7 pi over 3, which is actually up here. It's more than one revolution. The sine value is positive, so I get an actual value there of 5.58 once I take the square root. So I get that point right there. And I'm going to connect those with a smooth curve. And then when I plug in 5 pi over 4, I get 6 again. Well, I'm going to connect those with a smooth curve, and rather than continuing plugging in points, I see the symmetry here. I see it's going to be symmetric to that line, theta equals pi over 4, so I'm just going to draw in the bottom half here. And there we have the lemniscate, r squared equals 36 times the sine of 2 theta. So this is how you graph these polar equations. Part of it is knowing what the graph is going to look like beforehand, but the other part is just kind of finding some values.